now discuss the topic of dynamic multiple issue processes or out of order processes. The content is mainly taken from Computer Architecture Quantitative Approach by Hennessy and Patterson, especially chapter 3.4 onwards. You can also use chapter 4.2 and 4.3 of Shen and Lipasti. There is a very good video lecture series by Professor Ono Mutlu in this particular course, and he covers a wide range of topics from lecture 14 to 17a, starting from pipelining to out of order execution. So we'll first discuss the need for dynamic multiple issue processes. So first let us look at this piece of code here. This is on a single issue pipelined processor containing 5 stages. So we have a div operation whose result is used by the next instruction add, and then there is a sub instruction whose sources are independent of the previous instructions. The diff takes 800 picoseconds for the EX stage, the add takes 100 and the sub takes 100. So what is the latency of a single EX stage of this entire processor? So that should be equivalent to the longest stage, which is 800 picoseconds. Because all instructions are supposed to go through that particular stage, and we have to accommodate the slowest instruction, which is the div instruction. So the EX will contain a delay of 800 picoseconds. Now there are what are called as diversified pipelines, or it's also called multi-cycle execution. So for example, if you have a diverse set of instructions which take different latencies to execute, what we could do is we could have different execution units or different hardware resources for that instead of making them go through the same ALU. So you can make them go through different ALUs which perform different operations, because it is inefficient to make all instructions go through the same stage with the same delay. So you could have parallel pipelined ALUs, and you could send the different instructions to their respective functional units, and then this will help reduce the clock time. Now, how will we do this? We'll look at it. Now, let's say, for example, the add instruction takes 1 cycle to execute. So can it go ahead and do the mem stage and the write back? Or does it have to wait for the other instructions to finish the write back? So we'll look at that. So for example, now if we have this kind of a diversified pipeline with different functional units, some of the things we should consider are, what are the different functional units you need? So in the previous example, we saw there was an integer add, branch, muldiv, and load store. So if you have a load store, it will go into this pipeline. It will take 8 cycles to provide the result. The multiplication and division will go into this particular functional unit, and they'll take 8 cycles to complete, and so on. So now, how do you identify what are the different functional units you need? So this should basically match the different types of instructions that you have in the program or in the ISA actually. Then how many of them do you need? So in the previous example, we saw we had 4 functional units. So how many of them do we actually want in our architecture? That depends on how many parallel execution units do you need, and how much amount of parallelism is there in your program. Then the typically used kind of pipelines are integer execution pipeline and floating point pipelines. So if you have an integer unit, you send it to the integer execution units. And if you have floating point instructions, you send them to the floating point execution units. Or you could have, like we had in the previous slide, integer floating points, load stores, and branch pipelines. And you could also have buffers between the stages. So now, having gone through this particular example, now let us see how it is issued on this processor. So now the division takes 8 cycles to execute. Now the add needs the result of diff. So assuming that we have forwarding, we are going to forward F0 after the last execution stage. Therefore, the add has to stall here. And because this is an in-order pipeline, that is, instructions execute in the same order as they are fetched, the sub has to wait till the previous instruction completes. So now, what is a disadvantage with this? The disadvantage is that the sub instruction, although it has all of its operands available and it does not have to wait for any previous instructions to complete, it still has to wait because the add, which is the previous instruction, has not finished or it has not completed its execution. So now what is the solution for this? Of course, we could have reordered this instruction. In fact, the compiler could have reordered the instruction. So why did the compiler not reorder the instruction? It may not always be able to do the reordering because it may not know the latencies during the runtime. So for example, the division has this amount of latency and the compiler may not be aware of it. Also, there are load stores which completely depend on the cache or the memory. So the compiler has no information whether the address to be loaded or the data to be loaded is in the cache or in the memory. And based on this, the latencies are going to differ. So for example, if the data is in the L1 cache, the latency would be less, whereas if the data is in the main memory, the latency could be very high. So depending on the runtime latency, the uh, the total latency of the instruction changes and the compiler has no such information, so the compiler may not be able to reorder all the time. So that is why you may have instructions such as this issued to the processor, and instructions which are actually independent will have to wait. So what we do is we are going to do reordering in the hardware at runtime, and we're going to make the instructions run in an out of order fashion. So basically, we are not going to reorder the code because the processor only has information about what is instruction 1, 2, 3, and so on. It cannot look ahead of the sequence. For example, it does not know what is instruction 100 until you fetch it. So basically, reordering cannot be done in the same sense as it is done in the compiler because compiler has a look at the entire instruction set and the instructions that are in the program, and it can have idea of the future instructions, whereas the hardware does not have such an idea. So what we do is we do what is called out of order execution. So basically we can see sub and then we can start execution of sub ahead of add, and that is what is called as out of order processing or out of order execution, and that is said to have much better performance than the best code that a compiler can generate. So out of order processing is necessary and it has been used by most modern processors. So what is meant by out of order scheduling? So basically, how do we start executing the sub instruction while the add is waiting for the F0? So basically, this is what we do. The add is still waiting, it's still stalled, and it is still waiting for completing its execution while the sub has started its execution. And of course, the write back is not going to happen here. And that is because we don't want to be overwriting any data before the previous instruction writes it. So this is what is called as in order write back. So we are going to write back in the same sequence as the instructions are fetched. So the first instruction has to complete its write back, then the second instruction completes, and then the third instruction completes. So we are going to follow the same sequence, but we are going to start the execution early. So now what is the advantage of executing sub? So let us look at the two scenarios. So in the first scenario, you're stalling all the instructions. So this is the normal scenario wherein you're stalling all instructions and waiting for the add to finish. Now consider the scenario where there is some other instruction mul which has the same amount of delay, that is 8 cycles of latency for the EX stage, and it has a dependency on the sub instruction. Now what is going to happen is all these instructions are delayed, and then the mul is going to take another 8 cycles after this particular stage to complete its EX stage. Now, if we were to do this out of order scheduling, that is, if we are starting the sub instruction at this point in time, So we can always forward the F12 content to the mul instruction and start its execution right in the next cycle. So this is going to take a while to finish, and then we are uh, good to go and start the write back right after the sub does its write back. So this is a huge advantage of doing this out of order scheduling. In fact, what is out of order is actually the execution. So it's actually called out of order execution. So now how do we do this in hardware? So this is an example of a diverse pipeline. A diverse pipeline contains multiple parallel functional units. We are considering a one issue processor or a one wide processor, which means you can only fetch one instruction per cycle. And we have multiple functional units with variable latency. So now we are going to introduce a stage here, which is called the dispatch or the issue stage. It's also sometimes called the rename stage, wherein the renaming occurs in this stage. Now, let us say that we have fetched div, decoded it, we have renamed it, and we have dispatched it. We have dispatched it, meaning we are sending it to the functional unit. So like I said, there are three names for this: rename, dispatch, or issue. So we can just stick to the name that is shown here, which is called the dispatch or the rename stage. So we have dispatched the div to the functional unit. Next, the add is fetched, decoded, and it is renamed, but it is waiting here. It cannot be dispatched to the functional unit because it is waiting on F0 to complete. So add is waiting and cannot get dispatched. Now we want to dispatch sub. We have fetched sub, decoded it, found that it is independent, and we want to dispatch it to its functional unit. Now, how are we going to do this? What we will do is we will make the add wait in a buffer. So we will add a buffer here, which is called the dispatch buffer, or it's also called the reservation station. This is a more technical term. It's called a reservation station. So we're going to move add to this reservation station. We're basically moving it out of the way so that sub can go ahead and get dispatched. So once we have an instruction which is waiting for an operand, we're going to make it move to what is called the reservation station. The add will wait there as long as the F0 is not available, while the sub is getting renamed, dispatched. It goes through the buffer. It does not wait here because it is independent, and it is getting dispatched to its functional unit. Now, once the functional unit completes its execution, the sub needs only one cycle to complete. But like we saw in the previous pipeline diagram, we are not going to write back the result to the register. We are going to do what is called an in order complete or in order write back. We will see what are the issues with out of order write back and if processors do that. But currently, let us assume that we are going to do an in order write back. So we have to make the results of this sub instruction wait until the previous one has done this write back. So what we will do is add another buffer here. This buffer is called the reorder buffer. The sub writes its result not to the register, but it is going to write it to this reorder buffer. It's called the rob. And the results are going to wait here until the add, that is the previous instruction, does its write back. Now, that is why we have two stages here. The execute stage is what we all know. This is the one which goes through the ALU or the functional units. The next stage, wherein we write the result back to the reorder buffer, is called the complete stage. So basically the execution is complete. So earlier we used to call this write back, but now we call it complete. Of course, there is a memory section here which is not shown. The memory is going to happen as it used to happen in a normal processor. After that, it's going to have a stage called complete, where it will write the results to the reorder buffer. And then the last stage is called the retire stage or the commit stage. This is equivalent to our write back stage where the results are written back to the register. So these are the different steps in this processor. So normally we would have multiple reservation stations. So this kind of diagram is taken from Shen and Lipasti. So normally you would have multiple reservation stations for the different functional units. So the add and sub will have its own reservation station here. It's also called RS1. The memory stage itself will have its own functional unit and the reservation station. The floating point similarly and the branch, they have their own reservation stations. So finally, this is called the front end of the processor, the fetch, decode, dispatch, or rename. This is the in order dispatch. All of this is happening in order, fetch, decode, and dispatch. Then the execution is happening out of order. The completion of the execution is happening out of order, whereas the commit or the write back is happening in order, and this is called the back end of the processor. So that's how we come up with the 7 stage pipeline, the fetch, decode, dispatch to the RS, all of them happening in order. Then you have the issue from the RS to the EX. So issuing the instruction from the reservation station to the execution unit is called the issue stage. So the instruction is basically issued to the functional unit. Then you have the EX stage. So EX also has the memory stage. So basically the load stores. Load stores are handled slightly differently. They have a queue called the load store queue. So we'll come and discuss that later. So the execute includes not just the ALU functionality, but also the memory operations. Then you have the complete stage wherein the EX has completed and written the results to the ROB or the reorder buffer. And finally, the results are written from the reorder buffer to the architectural register file, and that's called the commit stage. Some books also call it the retire stage. So of course, now you know which of these is done in order and out of order. So finally, to sum up, what was the motivation for out of order execution? So this is also called dynamic pipeline scheduling because the scheduling of the pipeline is happening at runtime dynamically, and that's why it's called dynamic pipeline scheduling, or it's also called dynamic issue processors. So basically, we came up with a question of how do we start executing the sub, which was independent of the other instructions. So we made add wait in a reservation station till its operands are available. So what is the structure of the reservation station? What is the structure of the ROB? I'll describe that in the coming lectures. Then we fetched, decode, and dispatch sub into a free functional unit. So this is important. You should not have a structural hazard. So if the functional unit is free, we are going to issue the instruction, which is independent. And like I mentioned here, we check for structural hazards and if there is an absence of the data hazard. And then finally, we are going to issue the sub instruction. So we introduced a stage called issue, wherein we issue the instruction from the RS to the EX stage. And that is because the operands are available and we execute the instructions out of order. The important point is we do not commit the results of sub to the register file. We wait until the previous one commits. So we wait until all the previous instructions in the ROB have written the results back, and that is why we call this the in order commit. So this is the summary of what we have discussed so far. In the next lecture, we're going to discuss an algorithm which is used for out of order scheduling that's called the Tomasello algorithm.